Hi class, this is number 4 on 7.1. A population has a normal distribution. So now we're no longer working on uniform distributions, but normal distributions. And it gives you the mean of the distribution and the standard deviation of the distribution. So that just means that it's bell-shaped. The data, instead of everything in the probability distribution having equally likelihood and everything having each bar graph having the same height, like we saw in each value of the variable and each outcome of the probability experiment being the same probability and having the same height. Now they have the distribution of the probability of the probability experiment is now going to be uniformly distributed. So it's going to look something like this. So on the tails, things are going to be less likely to happen. And then in the middle is your there's a higher probability for the things that are in the middle. And the other tail, then you have the probability of these things happening is less as well. Okay, so that this is, instead of being uniform like we saw in the previous section, now it's bell-shaped. So when we had a uniform distribution, it was really easy to calculate because it was just finding the area of rectangles, and that was easy for us to do. So this mathematically, it's nothing that you have to concern yourself with, because the math has been invented already. I'm not expecting you guys to invent the wheel already. But our job is going to be finding the area, just like we found the area underneath this rectangle. We're going to be finding the area under this normal distribution curve, and it actually has a really complicated mathematical formula, like the curve itself actually does. And it's actually kind of a complicated thing to actually find, but modern day calculus has allowed us to find this area under the curve very easily. So thanks to calculus. So we're interested in the area, and just so that you know, the mean of that distribution is they're right in the middle. The peak of that hill is going to happen at 32, and then it's one standard deviation is 37.2. So that means right at the inflection point of this going down is right here is 37.2 spaces in front ahead of that. So that's going to be like, what is that? 32 plus 37.2 is going to be what? 69.2. So this is where this inflection point where it's halfway down the hill is 69.2. Okay. And so the area that we want to find under the curve is between 34.7 and 35.8. So it is located between the 32, the mean, and one standard deviation above the 69.2. So, but because we can kind of see the spacing a little bit better now, we can kind of see that that's going to be somewhere like between right here and right here, right? It's a really small region. So that's what we're trying to find the area of. And under the whole entire normal distribution, under the whole curve is the one hole. So we can kind of guess what this little tiny blue region might be. I mean, it doesn't seem like it's that. I mean, it is part of the taller part of the rectangle, so that might make it big, but it's not very wide. So we can just get a visual representation of what our answer might be. But now let's see how to actually calculate it. Now, like I said, before calculus, this has been a very complicated thing, but we're just going to plug this into a calculator, and it's going to be pretty easy and fast and straightforward. So here we go. We just go to stats, and then we go to distribution, DIST, And then instead of going to binomial distribution like we were doing earlier, we're going to go to normal distribution. It's going to be very kind of similar. It's going to ask us for two things, the mean and standard deviation, which is exactly the two things that they had already given us in this problem. The mean is 32, so I just put 32, and then standard deviation is 37.2. And then see, there's no way that they could find find our answer, because the mean and standard deviation really show us, especially the standard deviation really shows us how the shape of that bell curve and how tall and how how tall it is, and just kind of the shape of it. And mean is where it's focused, where the high point of it is. So if we don't know that, then how is it? Then the computer just can't calculate what we want for it, So we always are going to choose CDF. They automatically are saying they're telling us, see, from negative infinity, if you look at the area under the curve from negative infinity to positive infinity, it's one hole, and they're telling us that. So we don't want that. We want between 34.7 and 35.8. So all we have to do is type that in, 34.7 and 35.8. And there we go. There's our answer. 0.01175. Let me make sure I typed everything in correctly. 34.7, 35.8. Okay, let's just double check our answer. Yeah, 0.0118. Okay, if you do these calculations more, some statistical, I think they're saying these two answers are this one or that one. I'm thinking, depending on the method that you used, you might get a slightly different answer, just a little bit, but it's close to net for government. So our answer is the 0.0118. Oh, and they said to 4 decimal places, yes. So we did get that. Let me just double check again that we got the 0.0118. Yes, okay. Then they said find the probability that a random variable, find the probability that a randomly selected sample of size n has a mean between 34.7 and 35.8. Find the probability that a randomly selected sample of size 186 has a mean between 34.7 and 35.8. Oh, it's the mean is between. This one was just find the probability that a single randomly selected value. Oh, okay, is between 34.7 and 35.8. Now, with this one, they're talking about the distribution of a mean. And something that we find out is that you'll have a distribution of certain values. And they could be let's say they're just the number of it's a distribution, and it's the number. This represents the frequency distribution, which is equivalent, if we write it as in relative frequency, that it's equivalent to the probability if they're equally likely events. But if it's a frequency distribution of some item, Then what happens when we think about getting a sample? Let's say you have a population of men, and you're focused on their heights. The probability of finding a sample that has, one guy that is, let's say 6'4", the probability of getting, let's say you take a sample of 100 men, and the probability of getting at least, well, not a sample, let's just say, what's the probability of finding one single guy that's 6'4" or something? It's not uncommon. You'll run one into one. But the probability of taking more than one, now this is kind of like going back to probability when we were talking about finding the probability of one event happening, right? Just find the probability of taking a dice and like rolling it and landing on a 1 or whatever. It's a 1 out of 6. But what's the probability of now rolling 2 dice and landing on? Now the probability is there's 2 events, that's 1/6 times 1/6 to get both of those events happening. And so like, it's like now they're finding the probability of 186 values and them having a mean between 34.7 and 35.8. So that's kind of equivalent to thinking about, okay, well, yeah, my likelihood of finding one guy or a random guy. If I picked a random guy and the probability that he's 6'4", it's probably pretty likely, but that you could, randomly pick a guy that's 6'4", it's probably pretty likely. However, picking a sample of 100 men and having the mean of those men be 6'4" is much more unlikely. So you'll notice that the uncommon events. So let me just show you a picture really fast. So let's think about, it's easiest to think about men's heights. That's the best way for me to describe. So if we have a frequency distribution of men's heights, and let's say the average guy is 5'8". I actually don't know the mean height, and that means the mean would be here, and that means the tails would be over here, right? Well, if this is the frequency distribution of heights, if we look at if we look at the sampling distribution, which is if we took a sample of maybe say 100 guys, and the larger the sample, what's going to happen to this graph, if we took a frequency distribution graph, what's going to happen is all of the mean of the sample is going to come back a lot closer to the mean of the original frequency distribution. And the picture is going to look a lot more like this. The spread, so this is the original distribution, original frequency distribution. Then the sampling distribution. And what I mean by sampling distribution is they took, now instead of taking one random individual, now they took 100 in this situation, they took 186 random individuals, and then they took the mean of those. So, and then they recorded them down, and hypothetically, they took 100 samples that were of size 186, and then they from all those 100 samples of size 186, then they recorded the mean from each of those samples, and then they did a frequency distribution of all the means, and the mean that came up most common is the one that you'll see is at the peak here. that I draw. And so the most common standard mean is going to be actually the same as the most common in the just if you were just picking them one at a time in the original distribution. But what's going to happen is in the tails, the really short men and the really tall guys, you're not going to get that as often as being a mean of 186 people. You're going to get more the mean of the sampling distribution down here is going to be the same as the original distribution, 5.8, but the spread is going to be a lot smaller. Ooh. Because you're less likely to find a sample of 186 people and have it be a really oddly large height or oddly small height, like 6'4", like I mentioned. Because so these tails are going to be really short and really, we have to be really concentrated. Almost everything is located in the center. So while the original distribution kind of looks flat and you kind of have gradual tails going off to both sides, this one has really tall center and then like really short little tails on the sides. Because it's, like I said, here's 6'4" over here. It's just not that common to find a sample of 186 men and have the mean average be 6'4". That just doesn't happen very often, right? So that's the height here of that rectangle is gonna be very short, almost non-existent actually. All right, so my point in telling you this is that you need to focus, this calculation is going to be different because we're finding a sample and we're finding the mean of a sample. So very similar to how before, when you're picking one, when you're rolling a dice once, the probability is 1/6, but if you roll twice and find the probability of getting 2 6s, that's a different type of calculation, right? So we have to think about that too, that they performed this 168 times. And so we're getting a different distribution here. And the formulas for this are the standard deviation, the mean of, they call this the sampling distribution, and they usually use of the mean, sampling distribution of the mean. So they usually use a little x bar. So when I put mu x bar, I mean the mean of the sampling distribution is equal to the mean of the original distribution. And the mean of the original distribution, I'm going to use a mu symbol. So I'm just saying this 5.8 is here, and the 5.8 is going to stay the same as that. The height of that rectangle in the original distribution is the same here, which means you're going to use the same mean that you used before in the first part of this problem. Now the standard deviation of the sampling distribution is going to be smaller. See how it's thinner, and it's a thinner spread, right? It's thinner hill. So that's going to change, and I believe, and I have to double check this, but it's this. It's the original standard deviation over the square root of n. So the n really affects it. If there's only one person in the sample, notice that it's the same standard deviation as you have, and that's what it should be, right? But if you have like 4 people in your sample, then it's just divided by 2. So it's just, it's similar, but the larger your n, the larger your n, I believe, like what I'm thinking, then the larger this denominator and the smaller the standard deviation, which is the smaller the spread is. It's just getting tighter and tighter and tighter. So yeah, the larger your sample size, the more you're going to have all of your samples coming back to the mean, really close to the average height of the guy. so that's what we need to calculate here. We need to take, so we can, now what I'm gonna do to calculate this part B, I can pull up my calculator. I'm gonna still use normal CDF. I'm gonna still use the same, here, I'll just like output everything here. I'm still gonna use the 32 for the mu, because like I said, I wrote out here, down here, I wrote that the mu of this new sampling distribution to find the mean is the same as the mu in the original distribution. So we can still use the 32, but now I need to calculate, I need to take the standard deviation originally there, the 37.2, and I need to divide it by the square root of n, and n is 186. Okay, and then I just do that calculation. Let me just do that. I might be able to even put that in. Maybe I don't even have to do any calculations because maybe we can just put it in. So it is 37.4, is it 30, or maybe it's 37.2. Divided by, maybe it'll let me do square root. Maybe it won't, okay, yeah, it will, okay. Over here, I can click on square root of 186, right? Okay, yeah, I don't even have to put that and find that decimal. If I just put the whole formula in right here, it'll do it for me. Okay, let me make sure that 37.2. Yeah, 37.2 divided by the square root of 186. Now I just have to put in that, and now I have my answer. It is 0.079. So let's just double check that. 0.079. Yep. Mm-hmm. Oh, and to 4 decimal places, it would have been 0.0793. Yep. Mm-hmm. 0.0793. Yeah, that's exactly what we got. So when they ask you, what is the likelihood of the mean of a sample being between those, then you've got to use the sampling distribution of the mean. And you have to use these formulas that I just gave you as your mean and standard deviation, right? It's not really a formula for they're just saying mean is the same there, but this is when you have to do this calculation, right? Okay. All right, well, I hope you found this very helpful and have a great day. Bye.